All right, this is Unit 5, Target 3. Use conservation of momentum to analyze the system of objects. And we're going to break it up into 3 different parts for you. For recoiling objects, for inelastic versus elastic collisions, and motion of center of mass. We can certainly ask questions about all these things, but this is just to help you study and organize the target a little bit for you. So the first one, let's look at recoiling objects. So A, recoiling objects. With this target, we are going to put everything in our system so that there's no outside forces. So the first kind of assumption, big idea, is no outside forces. So what does that mean if there's no outside forces on the system? That means momentum is conserved. So another way to write that, if I want to write that shorthand, the initial momentum of the system is equal to the final momentum of the system. So momentum is conserved. The momentum before is equal to the momentum after. So here's an example. We have 2 carts here. I have the spring loaded, and they're going to recoil. So usually, they're going to not be moving initially, and then they're moving. Now let's check this. So initial momentum of the system was 0. They weren't moving. So then how is that possible? Because afterwards they were moving. Didn't the momentum have some system? Or didn't the system have some momentum? You have to remember momentum's vector. So as these are recoiling, you have the momentum of this one going this way. The momentum of this one is pointing in this direction. Those are opposite directions. Since momentum is a vector, those momenta can cancel each other out. So however much momentum is going this way, for this cart, we have the exact same amount, but the opposite direction. So the total momentum is still 0. We've got to remember momentum's a vector. So initially with these problems, the initial momentum is 0, but we have some momentum. If we want to draw a little diagram of this, we have one car here, the momentum of A is maybe going this way, and the other car here, the momentum of B is going this way, and the magnitude of each of those, the momentum of A is equal to the momentum of B. They're just in different directions. So you are going to have momentum conserved. Start with 0 momentum, have 0 momentum afterwards. A lot of times we may write this in an equation. Well, initially, the initial momentum was 0, and the final momentum was, well, the mass of A times the velocity of A final plus the mass of B times the velocity of B final. And again, these are going to be going in opposite directions, so they're going to cancel each other out just perfect. Mechanical energy is not conserved in these explosion collisions or these recoiling objects, because right now there is, I guess we can think about the spring, but let's say if there was gunpowder in there or something and we had an explosion, we have no mechanical energy, and now we have some mechanical energy. It came out of nowhere. Well, it was stored differently in the system before that. So energy is still conserved, but mechanical energy is not conserved. All right, so that's recoiling objects. The next one, inelastic versus elastic collisions. We'll do that on here. So B, inelastic versus elastic collisions. Inelastic is when mechanical energy is not conserved. So inelastic, mechanical energy not conserved. Some examples of that, when mechanical energy is not conserved, is these explosion problems. So where you have, the explosion problem would be one. Another one would be just a regular collision. So we go like here, and we have some collision, even if we don't have the springs involved. We have this collision here. The momentum is going to be conserved, but not the mechanical energy. So it's going to have less energy afterwards than it had before. And why is that? Well, usually when we hear it, you hear that sound. So there's some energy dissipated as sound, heat, and also like in a car crash, if you have the deformation of the objects, or with clay, the clay is deforming. So that's an inelastic collision when mechanical energy is not conserved. An elastic collision is the opposite of that. So elastic is when mechanical energy is conserved. So mechanical energy is conserved. This really only happens in like perfect physics world. We can approximate it with a few things. One, if we have these magnets so they don't actually touch. And now listen, you don't hear them, this big collision, really loud collision sound. And so we're not losing as much energy to sound or to things getting deformed. But we will have elastic collisions when we'll just pretend, like, okay, pretend there's no energy loss to sound or deformation or heat or any of those things. So the third one is the motion of the center of mass. So let's do that over here on this board. There's a collision for you. So C is the motion of the center of mass. The thing you have to learn about this, you have to understand, is if you don't go in and mess with a system, if you don't go in and exert a force on it, the velocity of the center of mass is always going to stay the same. It's not going to change. This just goes back to first law in Unit 2, where if there's no net force on an object, its velocity won't change. It's the same thing. So the velocity of the system's center of mass. So when we say center of mass, we're just kind of saying if we have multiple objects, where about the average mass is. So here we have more mass, here we have less mass, so it would be closer to this one over here. We're not going to ask you to calculate exactly where that is. So some examples of this is carts exploding. So for here, if we started them together and let them go, beforehand the velocity of the center of mass, or the center of mass was here and the velocity is 0 of the system. And now, if I let it go, well, they're both moving, but again, those velocities are going to cancel each other out, and the center of mass stayed exactly in the center. Another example is when you and another student are on rollerblades or ice skates or on lab carts, and you're facing towards each other and you push off. The center of mass, the velocity of the center of mass of your system is still going to stay 0, even though you're both going opposite directions. If you have one object moving or two objects moving, so maybe we ask you about the velocity of the center of mass of this system. So what you're going to do is you are going to calculate the momentum of the system, so mass 1 and maybe velocity 1 initial plus mass 2, velocity 2 initial, and that is the momentum of the system. So what's the momentum of the system? Well, the mass of the system times the velocity of the system. So if you know, if both of these are moving, you don't have to do any fancy calculations. You can calculate the momentum of each of them individually, add them up. That's the total mass of the, or that's the total momentum of the whole system. And you say, well, that's equal to the momentum of the whole system. So let's divide by the mass of the system. So just the total mass divided by mass of the system. Things are not going to cancel on this side, but they will over here. And this will tell you the velocity of the system. And again, unless there's some outside force that goes in and messes with it, that will stay constant the entire time, before the collision and after the collision, unless there's an outside force. All right, so that is the overview of Target 3 for Unit 5.